This tutorial has the title DC Transfer Function Analysis. In this tutorial, we will continue to use the very simple circuit that was used in a couple of other tutorials in order to demonstrate some of the features of Multisim, but yet retain a simple circuit sufficiently simple that we can readily verify the results. So we have this circuit here. And the transfer function, as it's defined with Multisim, is actually a DC operation. I should say that this should not be confused with the more general title of transfer function, which is used in both S-plane analysis as well as steady-state frequency analysis. The term here for transfer function relates to the DC situation, in which three parameters are determined, and we'll talk about those three parameters very shortly. But we have this basic circuit here, an 18-volt source and two resistors in series. Now, when we determine the transfer function, and which I am calling, by the way, the DC transfer function, the voltage here is irrelevant. It can be any value that you so desire. In that sense, it is similar to the DC sweep analysis in that you specify the voltage in that particular case separately. But in this case, there is no voltage that even relates to the results. What you get really is the transfer function relating the output voltage over the input voltage. In other words, you get the what in this particular case would be a voltage divider ratio. Now, if you look at this particular circuit and you define the input as the voltage at node N with respect to ground and the output voltage as node out with respect to ground, and calculate the voltage division, that is V out over V in, you should get 3 ohms over 6 plus 3, which is 9, or 1/3. So if this were 18 volts applied, you would get 6 volts out. However, what you're going to get out of the transfer function analysis is simply the ratio of output to input, which should be 1/3. Now, a brief explanation of the other two parameters are appropriate. First of all, the input impedance as it relates to this circuit will be the resistance that you see looking into the circuit. They use the term impedance, but it's really a resistive circuit, so you would see 6 plus 3 looking in, or 9 ohms. What is often confusing to students when they learn about Thevenin's and Norton's theorem is to determine the equivalent resistance looking back into the circuit. Now, to do that, you de-energize any sources inside. If you had current sources, you would replace those by open circuits. Let me make a comment about how you de-energize a voltage source. On paper, or in this case on a computer screen, you would replace the voltage source by a short circuit for analysis purposes. You would never do this in a laboratory because in some cases it could even be dangerous to short a voltage source. So on paper, however, you can replace the 18-volt source by a short circuit. That puts the 6 ohms in parallel with the 3 ohms as far as looking back from the output is concerned. And that is basically what you do. You look back into the circuit from the output terminals with all sources de-energized, and in that case the 6 and 3 are in parallel, which gives you 2. So let's see now how Multisim handles this. I'll go up here to the grapher icon, click on it, and all my possible analysis operations come out, and I'm going to come down here to the transfer function. As I mentioned, it's really a DC transfer function, but they don't put DC on there. So I will click on it, and you have to specify an input, which happens to be a source. Well, in this case, there's only one source, so you can't even find any other source. It's simply V source. You specify an output node, which is should be V out. Okay, V out is the output node, and V of 0 is the ground reference node. So we're going to determine the transfer function between V source and V out with respect to ground. And we hit simulate. Well, let me maximize that. And as was shown in another example, we can actually change the graph here by, if we wanted to have white background, we can do so, but I'm going to go back to the default black background. And we see the transfer function as 333.3 little m. Now, we know it's 1/3. The little m means milli, or 10 to the minus 3. So if you move that decimal point 3 places to the left, you get 1/3, or 0.333. Now, the input impedance, as already mentioned, is 9 ohms. And if you look back from the output, you have 2 ohms looking back into the circuit. So in effect, you have essentially done a Thevenin equivalent circuit as far as the output is concerned, with one exception. What you're getting is the actual transfer between the input and the output. So for a given input, you would have to multiply that number times the the source voltage, and in which case you would get 1/3 times 18, or 6 volts. So you can readily determine a Thevenin equivalent circuit this way. So that concludes this particular example.